Welcome to the Machines and Molecules podcast. Machines and Molecules hosts guests that have backgrounds in chemistry, biochemistry, and machine learning, and this time around, actually, industrial engineering, because our guest today is Carlos Härtel, whose latest station was as CTO of Climeworks. He also consults with Carbon Removal Partners and Spacewalk, two VCs that like to focus on technically hard startups. He's consulting governments in deep tech innovation, and I'm very much looking forward to the conversation with you. Hi, Carlos.
Hi, Ingmar. Thank you very much for the invitation. It's a pleasure to be here on the show, and thanks for having me.
How are you doing today?
Doing today very fine. Sitting here in Munich, weather is good. It's a little warm for the year, at least for this time of year, but otherwise I'm doing fine. Thank you very much. So I was looking forward to our discussion here today.
It's a bit warm for the time of the year. Unfortunately, that seems to be what we have to say for the foreseeable future. Each time we get to March, it's going to be warmer than the last March. You were working quite a bit on CO2 removal, especially in Climeworks, for example, which is a startup that works on direct air capture. And maybe you can explain a bit what all this CO2 removal is about and what the different approaches are to this.
Yeah, happy to do that, Ingmar. So carbon removal is a broad theme, a broad topic, and it refers to basically any measure you take to remove carbon dioxide from the atmosphere. And what usually, I guess, maybe the lay people would immediately assume as well, isn't that exactly what plants are doing all the time, like forests and mangroves and bacteria in the ocean and so on. And that is true. It's just that the amount of carbon dioxide we have as humanity pumped into the atmosphere totally overwhelms or exceeds the capacity that nature has to buffer this, to compensate for it and take on more. So there has to be, if we want to stabilize the CO2 concentration in the atmosphere, there have to also be technical ways of removing it. And that's what we would call technological carbon removal. And direct air capture is one of those. It's not the only one. There's also technologies to take CO2 directly out of ocean water or other water bodies. But if you take it directly out of the atmosphere, you could call it direct air capture. And direct air capture is, in a sense, an industrial technology. So you could compare it to filtering the air and taking out the CO2. So the simplest parallel to that would be your typical vacuum cleaner, where you don't want to take away the air. What you want to take away the dust in the air, and then maybe dust is lying around on the ground. So you suck in the air, you send it through a filter bag, and out comes at the back clean air. And after a while, your filter bag is full. Now you have the same thing in a direct air capture plant. You have a material that selectively binds to CO2, and once it's saturated, you have to regenerate it. In my example of a vacuum cleaner, I change the filter bag. I can't do that in my industrial plant, changing my materials all the time. What I can do is have this material undergo a so-called desorption process where it releases the CO2 again, typically under heat. That CO2 is then being collected, and if you want to store it away for good, it's typically sequestered somewhere deep in the ground. That's what the Climeworks plant in Iceland is doing. So this is fundamentally, some people call it a vacuum cleaner for the atmosphere in some sense. It's oversimplified, but I think it gives you a good mental model of what direct air capture really does.
Mm-hmm. It's a reusable bag vacuum
in a sense,
cleaner, right? Yeah. And you said you could also take it out of the ocean water. Why do people do that? Or if they don't, why don't they do that?
That does exist. The ocean is a somewhat more demanding environment. It's kind of like it's part of the biosphere, much more so than the atmosphere is. You may have some bacteria, and you may have germs and so on flying around in the atmosphere, but otherwise the atmosphere basically is a mixture of gases. The ocean is way more than a mixture of water with a few other substances, right? It's full of life. You have bacteria and you have all kinds of creatures in there that you have to take special care of. So it's a little easier to deal with gases than to deal with ocean water, but it's technically possible. The ocean water case, so the direct ocean capture, has another side effect or a side aspect to it. And that is the increasing CO2 content in the atmosphere leads to increased CO2 content in the ocean water, and that leads to acidification of the ocean. And that is a major problem that's coming our way. So if you can couple two things, remove the CO2 and maybe it may make the ocean a little less acidic, that could be a side benefit. Now, we oftentimes do not understand well enough all the implications that such interventions have. So there's a lot of research going on right now on what does it mean to the ocean chemistry, to the ocean biology, to the ecosystems in the oceans if I interfere with the liquid in which all this ocean life happens, if I interfere with that liquid. So technically you can do that. Whether it is safe to do it and where it is safe to do it and in which way is subject of ongoing R&D, but some companies have made good progress in this domain already. So you can expect to see more of it in the future.
And then the other approach could be, of course, not to filter something out of the air directly, but go to an exhaustion pipe where there's a lot of CO2 coming out and then take it out of there. What's the difference between this and the vacuum cleaner approach?
Yeah, thank you for asking, Ingmar. This is something which is often confused or not well separated. So the naive approach would be, before I take CO2 out of the atmosphere, where it's very highly diluted, it's 420 ppm is where we stand. It's 0.04%. So it's a trace gas, really, in the atmosphere. It's like argon. So it's almost none of it is in the atmosphere. It's just very highly active for the climate. So why don't I just go to where it highly concentrates and avoid it getting into the atmosphere in the first place? And that happens, and that is done, and that has to be done a lot more of. It's called carbon capture and sequestration, called CCS. While the chemistry and the technology has similarities between filtering CO2 from the air and filtering it from an exhaust stream, the purpose is radically different. The purpose of filtering it from an exhaust stream is really decarbonizing industry, decarbonizing steel plants or decarbonizing chemical plants or power plants if they are run on coal or natural gas. So this is one element of our journey towards net zero, is decarbonizing our current emission hotspots. But then if all of this is said and done, assume we are in 2050 and we basically have nothing left to decarbonize, the CO2 in the atmosphere is still at too high levels. So we have to bring it down over another couple of decades to levels which are, as we think at least today, and according to the science that we do have, avoids the critical tipping points in the geophysical system. So in some sense you can say, direct air capture or ocean capture in some sense deals with legacy emissions, while capturing it from the smokestack of some factory deals with today's emissions. These two need to go hand in hand. If I don't avoid emitting from a factory, from a power plant, I have a very hard time compensating for that if I just do direct air capture kind of like after the fact, after the mission has occurred. So these two things need to go hand in hand.
Yeah, probably directly capturing something at the point source is also cheaper in terms of how much CO2 you can take out per dollar spent. Is that right? Or
yeah, absolutely. Absolutely. The effort is money, so it's cheaper. But fundamentally, it's about the overall effort you have to spend is in the size of the equipment you build, the amount of materials you would need, the energy you would need to run the whole system, right? That's all is effort. And those efforts have different prices in different parts of the world. But fundamentally, if I capture it from a source that has about 30-40% CO2, as some industrial processes have, it is by definition, by basic thermodynamics, a lot simpler than capturing it from the atmosphere. And that's why when people confuse these two things and say like, well, why would I spend so much money on capturing it from the atmosphere when can I do it at a fraction of the price from the power plant? Well, the answer is you have to do both. There's not one is a substitute for the other. We have come to a point where we have to do both. This was not the case. Let me emphasize that. This was not the case 10, 15 years ago. 10, 15 years ago, removing carbon actively from the atmosphere or from the oceans was a pretty wacky idea. When the first direct air capture companies were founded, people said like, well, we're just decarbonizing industry and then we're good. We're staying below critical levels in terms of CO2 concentration. I don't think we need you. Well, it turns out we didn't do what we set out we would do. And so now we have to actually repair some of the damage done to the atmosphere over long periods of time. And that's where direct air capture, direct ocean capture comes in.
So it's in part also the inertia of societies to implement point source capturing of CO2 that leads to the necessity of direct air capture
exactly
type of
right.
technologies.
It's exactly right, Ingmar. Right? We have been dragging our feet, quite frankly, or as another metaphor has it, we were kicking cans down the road, always assuming something ingenious might come to our minds that would spare us the hassle of having to add all this equipment. If you capture CO2 from a point source, this is something which is fairly expensive. You were right in saying this is cheaper than capturing it from the atmosphere, but it's by no means cheap in an absolute sense. It's a lot of effort. Estimates we did in my previous work, when I was working for large international corporates in the energy space, we typically had the estimate if you have a coal power plant and you want to decarbonize its exhaust, you will probably need approximately a third of the energy that the coal plant produces just to decarbonize that coal plant. It means you have 3 coal plants running, one of them only runs for decarbonizing the triplet and the other 2 produce electricity. So you can imagine if you add these things up, right, this becomes an expensive proposition. And so in some sense, we said, well, we're gonna have some smart idea later on. We're gonna figure out how to do this more cheaply. Right now, it doesn't look so critical. However, we lost much time, unfortunately. And now it's urgent that we have to do both, decarbonize plus actively remove.
It would be interesting to go into this in particular, what needs to be done in order to accelerate innovation, especially for carbon removal. But maybe let's shift gears a bit and say, and maybe you can say a few words about what do you think is the most critical things that need to happen to make technically hard innovations possible and realized in society? Because technically hard innovations, they lack a lot of things. I think monies could be one of them. But from your perspective, what do you think is stopping these innovations most? What is the roadblock?
Yeah, so this is a couple of challenges that you have to overcome in anything which is hard tech or deep tech. Now, before I list those, let me say that the space that I'm most familiar with is fundamentally industrial technologies, which have their own set of challenges that people who are looking at basic materials research, or say simple systems that could be set up in a room somewhere, like in a diagnostic environment in a hospital, they do not have. But anyway, generally, I think the hurdles are always threefold. The first one is it actually doable or not? So there we may have some indications from lab experiments that a certain thing is possible. I mean, it could be a certain material class is technically feasible, or an application is particularly suitable for a new material class. But is it really? You can only find out once you are putting it into the real application. And what's missing in the lab is often that what kills you in real life, right? So scaling can mean I make it big, but it can also mean I'll just add all the other relevant application boundary conditions that do matter. Think of your example, what I just gave in the hospital, right? You all of a sudden have to have something which is part of a workflow of healthcare. Now, this has boundary conditions that you never know of in your lab. You only figure it out when you want to change the current workflow because you bring in innovation. Booms, it has all kinds of ripple effects. So systems are complicated in that they can surprise you. That's one thing. The second thing is, it now depends a little bit on size, is that it can be very capital intense to build even your first demonstrators. So direct air capture is just one example of many in climate tech. Whether it's large-scale electrolyzers or whether it's a decarbonized cement plant or whatever it is, there's only so much you can do on a small scale. And then you have to build it at a much larger scale. And many of these things do not scale easily. Even if you fundamentally, the process is the same and the design is congruent with your small lab design, just being bigger makes a huge difference. Physics and chemistry work differently at larger scales. And if you have a lot of capital that you need to have the certainty that the capital investment has a fair chance of success. I mean, basically monetizing on your investments later on. So the demand side needs to be clear. And we always see is kind of like, I would call it almost, it's not a conflict, but it's a bit of a chicken and egg situation that the people who are supposed to buy your solution and implement it may say like, but I first one haven't seen it demonstrated. Unless I've seen it run for a couple of years safely and reliably, I don't trust this can be done. But you say, well, I mean, I can't run it for a couple of years safely and reliably unless I have someone who's willing to give it a try together with me. That chicken and egg situation, especially if it's about large industrial systems, is very critical. The last point I would mention is that, again, is not applicable to everything that is hard and deep, but is applicable to quite a few things. That is your supply chain. Your supply chain needs to be convinced that what you're after is worthwhile going after, that there is a true market, there's true money to be made, and that they can scale up as you scale up. If your supply chain doubts that there is a sufficiently certain scale-up trajectory ahead of them and ahead of you as the young company, they will not make the necessary investments to bring down their contributions in cost and complexity, or basically just to develop something that doesn't exist. It can be as simple as a ventilator, but it could be something way more complicated than that. But very often your deep tech innovation needs dedicated components and subsystems which do come from suppliers. And those suppliers need to have as much confidence in your own growth potential than you and your investors have. And bringing this all together and linking it all up isn't easy. So the lab thing is the first step, and the small-scale demonstrator could be another very important step. But beyond that lies a lot of uncertainty about realities in the application, realities in the market, and the willingness of your supply chain to go along with you.
Yeah. This, I guess the chicken and egg problem, being able to run something reliably for a few years, this is probably more at the root than the supply chain problem, because if you are running something for a few years, then that already generates trust in the supply chain, at least to a certain degree. What do you see for solving this chicken and egg problem? What are possibilities to do that? Because this is seen also even in our case in the company, where you come along with a seemingly new technology, machine learning, and people in biotech have not used this for the last 2 decades. And they're like, yeah, if it works, then I'll use it. And just as you say, well, we can only demonstrate it works if you use it. So who could be the buyer for these types of technologies? Is it the state that could chip in here, maybe?
Yeah, so I think this is probably depending on the application and on the technology. It goes without saying that it's not uniform across all of those new materials or new technologies or new software systems or whatever. But fundamentally, it is the demand at the back end that pulls. And so there's various ways how demand can be created. You can regulate demand into an industry. And we do this regularly without even noticing it. So the demand for better catalytic converters in cars did not come because clients were asking for cleaner cars, but because the European Union and the US government and Japan declared or decreed that over time the emission regulation would tighten. And they give you even a timeline for it. This is how much NOx you can emit today, and in 5 years down the road, you can no longer emit this much. You can only emit half of it, for example. So this one way to say, like, these are practices we want to see established. We leave it to industry and the market to figure out how to do this best, but we have an outcome that we are going to regulate. The second thing is government procurement, which has always played a big role. In some countries, this is, in fact, like in the US, is the military, which plays an important role. But you could also say government procurement is a big portion. In the old space, when there was energy, was still a government-run thing. We had the old utilities also in Germany, which were not private companies, but they were really state-owned enterprises in a sense. In the healthcare space, you have it. In road, if you're building roads, or even if governments build new buildings, they can demand that in their own projects, only certain types of materials or only certain types of technologies will be accepted because they are more environmentally friendly or better for data protection or more long-lived or whatever it may be, or whatever objective they try to meet, they can basically put this into their tender documents and say, like, you can only submit if you satisfy those needs. And last not least, of course, it is that the government can, in some sense, say, in indirect ways, like we had it for renewable energies, to say, I give, in some sense, I give preference to renewables by guaranteeing someone that they can sell as much renewable electricity as they produce. They can sell it into the grid. I'm not buying it from them, but I make a law that forces the grid operators to take that electricity at a predefined price. And in that case, a market is generated. The moment where you have some certainty around the demand, the willingness of everybody along your value chain to take risks goes up significantly. because they do know what they do today has kind of an expiry date. It's not going to be around forever. It's going to be around for a couple of years, but things will change. And you get an early indication, especially from governments, that the world you're operating in is about to change quite significantly. So I don't want to say that always takes governments, but I actually think that the role of governments in creating demand is today not enough emphasized. Governments are often seen as entities that give money into R&D programs. So if you will, at the supply side, I give you, it's a risky research project, I give you some money, and so I lower the risk for you and so on. But that's fine, it just doesn't go out of the lab. It sits in the lab forever. You need to have the pull from the back end, not only the push from the laboratory. And at the back end, governments in many industries play an absolutely critical role.
Yes, absolutely. And one recent example of this is the carbon tax in the EU, right? That creates some demand.
Right, exactly.
Yeah, this is a very different approach from, say, forbidding flights under a certain distance. Like you could go ahead and say, okay, every flight has to be at least 700 kilometers has to cross 700 kilometers of distance, whereas introducing a carbon tax just kind of forces everybody to go in a certain direction, and how this is implemented is up to the participants of the market. This reminds me very much of machine learning systems, actually, where you're trying to force something into a certain direction, but you don't say you have to do it this way or that way.
Yeah,
I think that's a very smart mechanism, which is used very little in politics. I think also because you're experimenting with an extremely large system here.
That's true. That's true. Yeah. And if you're talking about uncertainties, right, if a country like Germany has 80 million inhabitants, you're probably having uncertainties around 80 million individuals who may or may not respond the way you expect them or you hope them to respond. Now, many will, but very vocal minorities can already wreak havoc on any even well-intended government initiative. So governments are indeed extremely carefully to directly interfere in the markets in some sense. And so they hope that kind of like nudging a little bit and kind of like trying to convince people and so on. This goes a certain way, but in many cases it doesn't go far enough. So I would say, bluntly claim, if we didn't have emission regulations, cars would emit today a lot more than they do. We might still have even lead in the fuel if it hadn't been outlawed. And we had never changed our famous ozone layer destructive chemicals against others if it hadn't been outlawed to use those. So this is, of course, this is the heavy-handed approach. You can do this sometimes when the threat is obvious and when the public good is so obvious as well. In other cases, it is more tricky. It is more difficult because people may themselves not see the immediate benefits. So they're like, why do you bring this onto me? Why do you make my life more complicated, right? I don't see the need for it. And with flights, we probably have that at this moment. Some countries experimenting with, I ban flights where there is a good train connection between two cities, but not many do it because they do exactly know the kind of like the pushback, right, or the response to it from the public and ultimately also from voters is actually hard to predict. It's not certain that goes well with the majority of your people. So policymakers have to be careful, but I just can always only remind them that they have such a critical role to play. They cannot dodge their responsibility for this. It may be hard, may be difficult. They may have to try their luck, but they just can't dodge it.
Yeah, definitely. So you also consult for governments and VCs about investments or government funding for deep tech innovation. What are the things you look at when you consult for VCs, say, and how is that different from consulting for government? Is it different at all?
Yeah, so my interaction with governments is very opportunistic, I'd say. If there is a meeting with government representatives, so I don't have a formal consultancy role to any government entity, neither in Germany nor somewhere else, but I just often run into policymakers. That's just a recurring thing. So what I would tell governments typically is that, as I just previously discussed, is you do set boundary conditions. You set the stage, and if there's nothing you can do. This is the reality, and you have to just accept it. So act accordingly. If you want more young companies to grow and prosper, you have to see what's my responsibility in defining the environment. in which they do act. It could be demand, it could be regulation, in some cases it could be R&D funding. I'm not against that at all. So depending on the circumstances, what's the best tool available in your own government toolkit? For VCs, I would typically say today, I mean, having seen so many young companies, that I would always recommend to look after, if you will, the essential technological core of what the company does. Especially in the clean tech space, you do find a number of young companies that fundamentally try to kind of plug together known components in innovative ways, but they're really focused exclusively on the application. I much rather like if a company has a core technology that they try to bring to bear on a specific application, but that may also have other applications elsewhere. So in some sense, a platform, if you will, or an enabling technology. So I'm not saying that you should hedge your bets. I mean, VCs are typically the ones that say, I'm all in, right? And then I hope that out of my 10 investments, one is going to pan out and make the returns I do need. But especially if you're looking into a very uncertain future around climate tech, where it's almost impossible to predict which direction regulations and industry adoption of stuff and whatever will take. It's just you are looking. It's a crystal ball that you're looking into. I would always recommend go for it. It's important. We need many new ideas in this space, but always focus on figuring out, is there a core technology in the midst of it that in case that one doesn't pan out the way we thought, could be used with benefits somewhere else. It just makes your investment so much more safe.
Is that a friction point with VCs? Because VCs, many VCs tend to really like somebody or a company that focuses a lot on solving exactly one problem.
Yeah, I think it is a friction point. At times, the first one is simply cultural. Say like, well, we're not in it to. So we're not an insurance company that hedges bets, but we are the ones. We are more bullish, or we go all in. And if we do believe if the pitch is good and the application is convincing and the team is strong, right, it's worth giving it a try. And so, yes, I do see that as a friction point. It is easier if you are, especially in a new climate tech or clean tech environment, where you kind of like project the demand society will have. It's speculative, but you could say if we're getting serious about protecting the environment and the climate, then this is the growth we need to see in certain domains. I mean, green steel or hydrogen or whatever it may be, or direct air capture, right? So you plot that as a pretty steep exponential curve and say like, look, and the supply today is next to nil. So there's space for everybody. And if we have a strong team and if we are not making major mistakes and if we hurry up why shouldn't we have a fair chance of winning here? So that story is easy and in some sense compelling. It just, in a sense, the problem with that is that future that you're basically having on the drawing board or in your pitch, right? This is chock full of uncertainties. Way more than many other futures that you can envision in diagnostic imaging or maybe in, I don't know, automotive, connected drive or whatever. Many things in the space of environment and climate are highly uncertain. And that's why I say in this case, maybe it's more justified to be a little more cautious. But yes, I agree. If you can't tell this one story that wins over the investment committee immediately, it's just like, well, this is cool and this is big and we want to participate in that, then maybe you have a harder time getting the funding you need.
Yeah, definitely. I often have the impression that many people that are investing into very complex subjects, they go by the heuristic of, if the person that pitches me the idea is absolutely convinced and confident, then probably it's a good idea. Because it's so hard to understand, and I'm not blaming anybody, because I wouldn't like to listen to pitches from, I don't know, industrial engineering, which I have no idea about, and then judge whether I should invest or not.
No, I totally agree with you. It's difficult. This is maybe easier if you have specialized investors that are focused on one domain and they develop a very deep understanding over time, then they get it immediately and see the value because they themselves can sense the context. But if you are in a broad domain, like, I don't know, AI or machine learning is a broad domain. If I bring it to bear on any industry, right, there's basically nobody who has done this for 10 years already who would be able to tell a good story from just something which is made up. So very often you kind of like fall back onto, does the team themselves Do they seem convinced? Do they seem capable? Do they seem sufficiently bullish about it? And can they tell me a story that is convincing? Or if I start drilling holes into it, will the story fall apart immediately? Or have they thought it through themselves sufficiently? So it's more weak factors, and I think they have value. It's just that very often it's hard to quantify the uncertainty that you have on a 5 to 10 year time horizon. So if you're making investments, and we have had many of those in the past in other industries as well, we say like, well, growth before profits, especially if it's about infrastructure stuff, with large equipment, your growth becomes extremely expensive.
Yeah.
You need a lot of capital to fund that growth, much more than you would need for a typical software platform. And so I guess one has to be careful about long-term, about tail risks. It has to make sure that there is something at its core that is just so valuable as a technology that this in itself is worth bringing to life. And the rest of it is a good story and is upside potential almost, and it's the thing that you want them to go after. But given that the uncertainties are so large, you may find out rather sooner than later that direction actually isn't feasible. And then you have to pivot. But where do you pivot if you have no core technology? Where to go?
Yes, absolutely. As we're coming to the end of our episode, the recurring theme in Machines and Molecules is that our guest brings a third M word that has to do with them or their work. Did you think of a third M word?
Yes, of course I did. Actually, I have two. So I have a third and a fourth. But let me start with it's kind of a bracket around molecules and machines. And at the left of it, at the beginning, if you're at the front end, is the humans, right? Nothing happens without the ingenuity of real human beings. No matter the amount of machine learning that we're trying to push, right? It is the human at the end of the day who has that it's the creative agent in it. So I would say as a proxy to have a word with M, I take mind as a proxy for the human. So mind, molecules, machines. And then in the spirit of what we discussed previously, it is the demand at the other end, at the tail end, that pulls all of this. No demand, no innovation, nothing. So I would put market as a proxy for demand, although market and demand is not the same, but as a proxy. So mind on the intro, and then at the tail end is the market.
Yes, these are both things that we discussed a lot. And I think they are extremely important in this. I mean, in my mind, especially market is the thing that would, if there would be market pull, there would be talent pull and people pull towards a certain solution.
Yeah, I totally agree. It's a discussion I'm often having, is that if you imagine, pick any domain you want. If you were certain that there was a demand for it, a lot of money and talent and intelligence and water would move immediately into the space. But if you leave it open and say like, well, if the solution is really good, right, then I'm sure there's going to be someone who will pick it up, right? That only leaves you with, I would say, the absolutely diehard innovators in this space that kind of like feel a mission to do it. Absolutely. But you need a much bigger system there. You need your investors, you need your clients, you need maybe your public support and everything else. So ultimately, I mean, the famous proverb is, it takes a village to raise a child. And it takes a company or a whole ecosystem to innovate. You cannot innovate yourself in a laboratory. You can invent something and you can have insights into scientific challenges, but the innovation piece is taking it profitably out there into the real life, and that requires a lot more than just ingenuity.
Definitely.
To come together.
People love working on these type of technologies. They just think it's a very hard life to pick if there's little market demand, or they have to create the market demand first. Yeah. Super. Thank you, Carlos, for being a guest in Machines and Molecules. It was a very pleasurable episode to record. So wishing you a great day, and hope to see you when you're around in Berlin or when I come to Munich.
Yeah, likewise, Ingmar. Thanks for inviting me again. Thanks for having me, and looking forward to seeing you next time, maybe here in real life.
Yes, super. Bye-bye.
Bye-bye.